Let us now consider transmission line resonators, where we will consider a section of a transmission line either open or short, and we will see that when the length of these sections of transmission lines are chosen appropriately, they will exhibit resonance, and near the resonant frequency we can model these transmission line resonators either in the form of a series RLC circuit or in the form of an equivalent parallel RLC circuit. So, transmission line sections of various lengths and terminations, open or short, can be used as a resonator. Now, let us consider a lossy transmission line of length L, and let us assume that it is terminated to a short circuit at one end. We also consider the transmission line to be of low loss with very small value of attenuation constant alpha. Now, this is shown in the figure. We have a transmission line section of length L, and alpha is the attenuation constant, Z naught is the characteristic impedance, and beta is the propagation constant. We are assuming this transmission line to be of low loss type, so that alpha is very small. Now, suppose we choose the line length L in such a way that at omega equal to omega naught, L is equal to lambda by 2. So, we are essentially considering a half wavelength short circuited section of a transmission line. Please note that this half wavelength will be only at a particular frequency. If we change the frequency of operation, the physical length of the transmission line will remain the same, and it will be depending upon whether frequency is higher or lower, the line length will be longer than lambda by 2 or it will be shorter than lambda by 2. So, the line length L is lambda by 2 at omega equal to omega naught. Now, for such lossy lines, we can write Z in to be equal to ZL plus Z0 tan hyperbolic gamma L divided by Z0 plus ZL tan hyperbolic gamma L. Now, in our case this ZL is 0, we have only this term left, because this becomes 0, this becomes 0, and these two Z0s cancel out, and therefore, when ZL equal to 0, Z in is Z0 tan hyperbolic gamma L. Now, we can substitute gamma as alpha plus j beta, and therefore, Z in becomes now Z0 tan hyperbolic alpha plus j beta multiplied by L, and this equation can be expanded as Z in is equal to tan hyperbolic alpha L, and tan hyperbolic j beta L will become j tan beta L. divided by 1 plus again j 10 beta L 10 hyperbolic alpha L. Now, we have considered the transmission line to have very low loss. So, in that case we can write alpha L to be much less compared to 1, and we can approximate 10 hyperbolic alpha L as alpha L, and similarly beta L can be written as omega L by V p phase velocity, and once we substitute omega equal to omega naught plus delta omega, this can be written as omega naught L by V p plus delta omega L by V p. Now, since we have L is equal to lambda by 2 at omega equal to omega naught, this term omega naught L by V p, this becomes pi, because V p will be lambda into f naught, omega naught can be written as 2 pi f naught, and L is lambda by 2. So, we will have omega naught L by V p is equal to pi. So, we have now beta L is equal to omega naught L by V p plus delta omega L by V p, and omega naught L by V p is equal to pi, and therefore, we can write beta L to be equal to pi plus delta omega pi by omega naught, and 10 beta L can be written as 10 pi plus delta omega pi by omega naught. Now, delta omega being very small compared to omega naught, we can use the approximation. First of all, 10 pi plus theta will become 10 theta, and then we can use the approximation for small theta, 10 theta equal to theta. So, we can write 10 beta L to be approximately equal to delta omega pi divided by omega naught. Hence, we can now write Z in, which is Z naught 10 hyperbolic alpha L plus j 10 beta L divided by 1 plus j 10 beta L 10 hyperbolic alpha L. Now, if you substitute 10 hyperbolic alpha L as alpha L and 10 beta L as delta omega pi by omega naught, we can write Z in approximately equal to Z naught alpha L plus j delta omega pi by omega naught divided by 1 plus j alpha L delta omega pi by omega naught. Now, here you can see in the denominator we have the product of two small terms, one is alpha L and another is delta omega pi by omega naught. So, this term can be neglected with respect to 1, and therefore, we can write Z in approximately equal to Z naught alpha L plus j delta omega pi by omega naught. Now, what we can do? We can compare it with the expression for input impedance of a series resonant circuit near its resonant frequency. So, which is given by Z in equal to R plus j 2 delta omega L. So, if we compare these two, this for a lambda by 2 short circuited transmission line section, and this Z in is for a series RLC circuit operating near its resonant frequency, then we can write R equal to Z naught alpha L and L equal to pi Z naught by 2 omega naught. And since omega square is equal to 1 by L C, we can find the capacitance C as 1 by omega naught square L, and we already have the expression for L, and this becomes equal to 2 by pi omega naught Z naught. Now, unloaded Q of the resonator, it is given by Q naught is equal to omega naught L by R. So, if we substitute L and R here, R equal to Z naught alpha L and L equal to pi Z naught by 2 omega naught, then we get Q naught, the unloaded Q of the resonator, to be equal to pi by 2 alpha L. So, smaller the value of alpha, larger will be the value of Q, and we will have a sharp resonance at omega equal to omega naught. So, we see that if we have a lambda by 2 section of a transmission line having small amount of loss, and the line is short circuited at one end, then the transmission line section can resonate at a frequency where the line length corresponds to half the wavelength. So, we continue our discussion on transmission line resonators. We consider another type of transmission line resonator. Here we consider a short circuited transmission line of length lambda by 4. So, for this type of transmission line resonator, we have at omega equal to omega naught, the physical length of the transmission line L is equal to lambda by 4, that means it is a quarter wave section short circuited at one end. Now, the line as before is assumed to be slightly lossy, that means having an attenuation constant of alpha and phase constant beta and characteristic impedance Z naught. So, for such line we have already seen that we can write Z in equal to Z naught tan hyperbolic alpha L plus j tan beta L divided by 1 plus j tan beta L tan hyperbolic alpha L. Now, what we do? We multiply both the numerator and the denominator by minus j cot beta L. So, in that case, when it is multiplied by minus j cot beta L, j tan beta L minus j cot beta L will give 1, and therefore, we can write Z in is equal to Z naught 1 minus J 10 hyperbolic alpha L cot beta L, and then this term will become 10 hyperbolic alpha L minus 1 into J cot beta L will give minus J cot beta L. So, Z in becomes, after multiplying by minus J cot beta L, Z in becomes Z naught 1 minus J 10 hyperbolic alpha L cot beta L divided by 10 hyperbolic alpha L minus J cot beta L. Once again, we consider omega to be omega naught plus delta omega close to the resonant frequency, and in this case, when it is a lambda by 4 transmission line section, beta L can be written as pi by 2 plus pi delta omega divided by 2 omega naught. Now, once we have this expression for beta L, we find that cot beta L, because of this pi by 2 term, it becomes minus 10 pi delta omega divided by 2 omega naught. Once again, since we are assuming delta omega to be small compared to omega naught, we can write 10 pi delta omega by 2 omega naught to be approximately equal to minus pi delta omega divided by 2 omega naught. And then we already have the expression for Z in. We can now make appropriate substitutions. 10 hyperbolic alpha L can be substituted by alpha L, and cot beta L we can make substitution minus pi delta omega by 2 omega naught. So, once we do that, we get Z in to be equal to Z naught 1 plus J alpha L pi delta omega by 2 omega naught. So, this minus and this minus will make it plus, and alpha L again plus J pi delta omega by 2 omega naught. Now, here in the numerator, once again we have product of two small terms alpha L and pi by 2 delta omega by omega naught. So, this term can be neglected in comparison with 1, and Z in finally can be approximated as Z naught divided by alpha L plus J pi by 2 delta omega by omega naught. So, this can be further written in this form: 1 by alpha L by Z naught plus J pi delta omega by 2 omega naught Z naught. Now, we identify that this form is of the input impedance is that of a parallel RLC circuit operating near its resonance. For a parallel RLC circuit near resonance, we have Z in to be approximately equal to R by 1 plus J 2 delta omega RC, which can be put of this form 1 by R plus J 2 delta omega C. Now, if we equate these corresponding terms, then we get R equal to Z naught by alpha L and C equal to pi by 4 omega naught Z naught. And once we have the values for R and C, we can calculate the value of L if required, and we can also calculate the unloaded Q. Q naught is equal to omega naught R C, and which is given by pi by 4 alpha L. Once again we see that low alpha L we have high values of unloaded Q. So, we find that a short circuited lambda by 4 section of a transmission line is essentially, it can be modeled as a parallel RLC circuit, and the resonant frequency will be determined by the length of the line at which it is lambda by 4. In this lecture, we have studied different types of transmission line resonators. In the next lecture, we will consider another form of resonator, which are waveguide resonators.